Okay. In case you needed any doubt that the meeting's being recorded, I decided to blast it to everybody. Sorry about that. Good afternoon, everyone. I have the same directions. If you go to the Sakai and go to the tests and quizzes, the in-class problems will be available there for lecture 3. As you're getting set up, I want to go over a couple of quick things. First, Coding Challenge 1 was officially assigned yesterday. The way it works is the knowledge that you need in order to be able to complete the assignment is either through the lectures or there's typically a little bit of a reading at the beginning where you have to do some problems and then do the code. So it's assigned on the Wednesday and then it is due the following Thursday. So not tomorrow, but a week from tomorrow. For the coding challenge, I have the link here, and one thing I wanted to show you is that there's a Sakai problem section. I want you to do the reading and then answer some questions. One crucial thing you'll see is that for those of you who are more inclined to learn from reading, there's some typed up stuff and some code. For those of you who are more audio and visual learners, after that reading, I repeat the same thing in a video. So here, these are the reviews. So if I go to call by reference, this is going to build on your knowledge of pass by reference. And I describe the code and what the output should be. And if you would like, there's a video that does the exact same thing. So each coding challenge is going to have a problem section and then a coding section. And the objection of the problem section is that if you understand everything, you'll be in really good shape for the coding section. So that's the first thing I want to point out. The second thing I can point out is at the top, I have little links that can help you get to each portion. So that way you can keep track of where you need to be. So for example, if you finish the C++ streams portion, but you're like, oh, I got to do this little recursion part, I can then go to part 4 and go straight to those directions. So it'll help you keep track of everything. 2 other quick things. So submitting your assignment, verifying your assignment, my apologies. For verifying that your code works, I have included a test script and I've given you directions on how to run that test script. And what's going to happen is when you run the test script, it goes through all the tests that will be used to verify the input and the output. So there's a portion of the coding that's your problems. There's a portion that's the test script. And then what the TAs do is they go into your code. They look to make sure that you're doing it in the approach that I was expecting. And then we'll give you feedback on your general coding practices. So that gives the opportunity to break that down, and that's all mentioned at the top. So you have that opportunity to verify that your code is working and exactly how we would do that. And then the last part, example schedule. I've mentioned this briefly in lecture 1, but I want you to take advantage of this. The goal here is to kind of show you how you can walk through and plan a bigger project. So that way, when you get into industry, you got to work in teams. There's a saying that I like to use in this case, pencils before pixels. A lot of your success in coding will involve, all right, I understand data structures. I have a specific problem. I'm going to try to break the problem down. So I have this sample schedule. So I have this little spiel about what you can do. And I can say, here's what you can do on this day. And it's a certain amount of time. And I have the time at the upper end of what I would expect. And the reason why is if you've taken that much time, please come find us in office hours. Please come find me, and we're happy to help. It's a guide to make sure that if you are struggling, we can reduce the amount of time that you're spending on an assignment. Remember, just take it as intellectual curiosity. It's not like as though I'm going to show up at your dream job and say you didn't do Coding Challenge 1 right the first time. Okay? We want to build your skill set so you're empowered in your future. So I have that as a sample. And I have a little note here on the slide. I looked in this morning. So there's that. And I saw that 21 students already have the coding challenge problems completed. So great job to those of you who are working a week ahead to get on the ball on that. The last part, I want to remind you all of the self-service extension policy. There's 8 coding challenges. Maybe you have the opportunity to use 2 self-service extensions. you have to ask for it by 24 hours before the deadline. So by midnight a week from today. If it gets into Thursday, my policy is that I don't grant extensions after that. So please take advantage, please plan ahead. And if you're getting to the point where you're planning ahead and you realize you're starting to fall behind, that's where you want to take advantage of a self-service extension. Does anybody have any questions on this before we start going into lecture? And again, just like last lecture, I have this Slack up here. So if you want to ask questions, but you don't want to yell, or if you're in the Zoom room, please feel free to ask there. Okay, so what I would like you to do is I would like you to take 4 minutes and attempt problem 1. This is an opportunity to combine concepts with void pointers, character pointers, and then looking up on, as I say, you can look up on ASCIItable.com, and I want you to go through and see what you expect the output to be. So please take 4 minutes to do that. And if you have any questions, please feel free to share in the Slack, and myself and fellow classmates would be happy to help. Okay, so who wants to tell me what the correct answer is? What's the correct choice? Yes. I'm sorry? Go Irish. So in the choice is going to be, at the end, it's going to be E. And I want to go through and describe the difference in all of these different choices. So 32 in ASCII is a space. And then you have, I think it was 36 is an exclamation point, and then 10 is the new line character. So for those of you who are going to do this, the answer is E, and it starts out here. And the other crucial portion is it's not just Go Irish, it prints out the address of the location on the data heap and then the character itself. So it's printing out 0, 1, 2, 3, those are the last characters. And the crucial thing I want you to take from that is that it's measured in bytes, and a character is 1 byte. It's 8 bits. So it's going to come out like that. So that's why the answer is E. So what I want to do next is I have the code here on a website known as Online GDB. And what I've done in this particular code is that I have added in extra compiler flags, I have all the production quality compilation flags. And you're going to, starting this lecture, I'm going to really start hitting home on some of the important things that I want you to learn from the implementation of those flags. So here we have the code that was implemented. And what I would like to do is kind of go over and reinforce what's happening when we change from void star to char star, because it's going to be a big thing when we go into the construction of classes today. So first, here at line 8, see if I can zoom in, what do I need to do to change void star phrase malloc to a character array? What are the 2 changes that I need to do? Yes? Yes, absolutely right. So we have char star. And then the other crucial thing is, absolutely right. Very good. Good job. So the question I got a lot in office hours was, why are we doing this in front of malloc? Here I have the link in CPP reference. This is the actual description of malloc in C++. And what you'll see is it actually returns void star. So when it allocates memory, it says, all right, I've allocated memory and I'm putting there on the heap. And you're saying, all right, I'm trying to make it represent something. What is the value there? And malloc just goes, I'm pointing there on the heap. That's all I do, I point. So in order to tell the operating system that we want to interpret this memory as characters, that is why we have to cast in front of malloc, because it's returning a void pointer, and then we say, no, operating system, we want to be safe and reliable. We are casting to char star. Okay, does anybody have any questions on that? All right, so now what I'm going to do is I'm going to go through and we're going to take the rest of this and move it up a level of abstraction. So now what I want to do is I'm going to take, I want to take this character, and now I'm going to make that a character array. A character pointer. So now reference, all that's doing is it's just pointing at a specific character. So now that I'm moving it up a little closer to object-oriented, because of that, I can now get rid of all of these. And what this is allowing me to do is I'm saying, well, phrase is already a character array. We don't need to tell the operating system again, because we have informed it it's a character array, and we can add a little more abstraction, a little less procedure. So now what happens is we have +0, +1. The operating system is automatically interpreting that as multiply by 1 times size of character. And then these values were go Irish. So if I wanted to, I could go and change them. I could say G and O and keep doing that. And now I'm abstracting it a little way from the ASCII value, which is the binary representation of characters, to something that we can interpret more when we're reading it. So the last thing I want to do is add a level, go up a level of abstraction here. What's going on is that I am printing out the address. Now this is an important thing. Char star is a character pointer. However, in order to actually print out the address, this is when I would need to cast back to void. Does that make sense? Awesome. So I'm going to cast a void star. And now I don't even need this char star here anymore, because all I'm trying to do is print the specific character. So now I'm saying dereference the character pointer that I'm pointing to and give me the value. And then last, I can just say reference equals reference plus 1, because size of char is 1 byte. So if I run it again, provided I didn't make any mistakes, we see that we get the exact same result at a different level of abstraction. So now what I'm going to do is I'm going to take us even one level higher. We're going to do new and delete. So now instead of all of this, I can just say new character array, numchars. And that does all of the allocation of memory. It does all of the conversion from void star to char star for me. And now what I'm going to do is I'm going to take away this reference. And so I don't need that reference because I can now say phrase. First, I'm going to do Control H, replace all. And then here, instead of plus, what I can do is I can just do here. That's going a little slower than I did in my rehearsal. There we go. And if I do this all the way through, there we go, replace all. And then I go here, and I just replace this with brackets. And if I just go down here, instead of having to do this reference everything, all I can do is just say, I want phrase iter. And now it's going to print everything out exactly how I want it. Provided I didn't make any mistakes, which I did. Iter, just replace this with plus plus. And there we go, that'll work. And so if I get rid of this end L here, it's now just going to print out a string just like we did with hello world. Okay. Does anybody have any questions about the levels of abstraction or what it is that I've just demonstrated? All right, so I'll check the Slack. Doesn't look like we have anything. So the important thing is, as we're going to go over class construction today, the way that we structure a class and eventually how we structure these data structures we're going to learn have the same fundamental principles. And if you understand what's going on here with all these pointers in this code, you will actually get a stronger understanding of data structures. So I can click through this here. We did all this, did all that. All right, so there's one crucial thing I want to show you here. If I have this piece of code and I'm not using the production quality compilation rules, it will run and will print Go Irish, but it's going to give me a warning. So I'm going to run a command here, and I have this, I call it CPP pointer bad, and I just print it out. And when I run, sorry, let me bring this up here. CPP pointer no PQC, we're going to see that it's going to run, but it gives us this warning, deprecated conversion from string constant to char star. But it still works. And if you're like, okay, that's fine. But I'm going to show you an issue where this becomes a problem. And the problem, the solution to the problem, is where the idea of classes came from. So if I run this and I do it with PQC, it's going to say it's an error. The reason why it's important to address all warnings is because once you have a warning, you can no longer guarantee exact operation precisely how you want it. Something has gone out of the scope, and now there's potential of losing information. And so, which is what I just said. Okay, so what I want to do is I want to show you a piece of C code and where this idea of procedural programming and how it can be really complicated can cause issues. So what's going on here is that the International Standard Organization, they have a flag that they include called pedantic. And they really want to make sure that you're effectively allocating memory. So what's happening here in this piece of code is that I have allocated a character array just like we did. And then what I did is I went through and I just said, hello, phrase 0 is H, all the way through phrase 4 is O. And then I call the fprintf. And in C, if you want to print an address, what you have to do is you have to use the output specifier %p and then cast it to void star phrase. So what's going to happen is we're going to see an address, and it's going to print the value. And then I have a phrase equals noter. It's the same characters. And then I'm going to print out the new, and I'm going to print the address and the phrase. And so what I want to do is I'm going to run this, and I want you to observe what happens. Make C pointer bad. OK. Ooh, that looks really nasty. So let's see what happened here. So it turns out it ran old, just like we expected, with an address and hello. And you gave us new with an address and noter. But I want you to notice something. Notice how these addresses are different. Because when you did that, char star hello equals noter, it actually allocates a different location on the data heap. So what happens is that this big thing is known as a memory map. And it's trying to find the address that's stored in the register and compare it to where you have everything in the operating system. When we did that, it updated the value in the register. And what ended up happening is it's saying here invalid pointer, and we have 40075D, right? You'll notice that it actually matches the second address. So what happens is it goes to the register. It says, I'm trying to look for this address to free the memory. And it looks through the entire memory map, which you'll learn about in a lot more detail in operating systems. And it goes, I never allocated memory there. What are you talking about? Right. So what happens is the C++ compilation rules, in order to preserve effective implementation of memory allocation, has banned this. And the way we get around it in C++ is to use something that you might be familiar with if you've coded in C++ before. We use a type of class standard template library known as a string. And a string is just a vector of characters. And so what happens is I just do string phrase, go Irish, and it just prints the phrase out, and it takes care of all of the memory allocation and deallocation for me. Does that make sense? So instead of having to worry about these giant memory maps, we can just run make CPP string, and that does all the work for me. So one of the benefits, if you write a really good class and a really good data structure, a user should be able to take your work and implement it, and all of that extra stuff that you did underneath the hood to make their life easier, it's all abstracted away, and they're going to be happy. Okay, so here's the memory map. And here in the slides, I also talk about how you can see that there's the difference between the locations, and we solved this problem with standard string. So standard string is a type of class. So what is a class, and how did we come up with this idea in the first place? First, does anybody have any questions about that before I continue? All right, let me check the Slack. Okay, so we're going to go all the way back to 1736. For those of you who've taken discrete math, you might be familiar with a problem called the 7 bridges of Königsberg problem. For those of you who are taking discrete, this is something you're going to encounter later this semester. So the idea is the mayor of Königsberg they have an interesting problem. They have 7 bridges, and the question is, can you get everywhere in Königsberg by using all 7 bridges and never using one twice? And this is a big mathematical problem, and mathematicians would come all over the world and would try to map out different things and try to come up with different solutions. And then Leonhard Euler comes along, And he has a revelation that transforms math and eventually transforms computer science. He realizes that everybody's trying to start. I'm just going to start here, and I'm going to go across this bridge, and I'm going to try to solve the problem from where I start. And it hits him, it doesn't matter where you start. If you treat everywhere as some block of information, and you try to solve it just with any particular set of blocks of information, you can then break the problem down simpler, and that's how he solved it. And he initially called this the geometry of position, which eventually became graph theory, which is a lot of the data science. If you apply for the iTreads program that Dr. Chavla was talking about yesterday, you'll hit a lot of graph theory and being able to convey information. So you can kind of see this idea of a block of information. And that block of information he initially called a node. And we're going to talk a lot about nodes in class this semester. We can represent data in very much the same way. We can say a void pointer points to the base address of a data node. You created a data structure in FunComp or intro, the character array, an array of integers. It's a block of information. And then you were able to break it down into further blocks by saying, I am going to do size of when I move the reference pointer. Then, when you're done, let's say I no longer need this or I no longer want this piece of information, it's deleted from my library. We can use our understanding of pointer arithmetic to be able to load, store, and eventually delete operations. So what you want to do is you want to take this idea, what you've been learning about pointers, and apply this to how to connect data throughout the data heap. Very much the same way that Leonard Euler was doing in 1736 when he was working on this problem. And so we have a question in the Slack. It says, why was it that when you ran pointer bad, the computer was looking for a different address? So I'll just, as everybody's taking their notes, I'll just quickly answer that. So what happens is when I said hello equals noder, without strict ISO standards, the computer will actually allocate new memory with a new string. But because you're using the same pointer, you actually lose track of the other piece of information. So that's why, did that address your question? Awesome, good to hear. Okay, so now I'm going to move on to the next slide. And so what I want to do is I'm going to bring up this piece of code, voidtypes.cpp. And what I'm going to show you is how it creates pointers, but instead of everything being the same type, we're going to start to see how we can put pieces together when it's different types of information. So first, in voidtypes.cpp, just like we did before, we create a void pointer, and I just say size of double. And here, I just have my double reference. I put a number there. And then what I'm going to do is I just set the reference equals to numbers. And you're going to see why that line's important in the next couple of iterations of code. And what I'm going to do is I'm going to print out the double at the address. And then I'm going to print out the address that numbers and reference is pointing to. So for right now, we expect that all the three of those addresses that we're going to print are going to print the same thing. Does that make sense? All right, so let me run make void types. And we see here that everything happened as we anticipated. It printed the value negative 0.625 at address ending in 010, and the address of the two pointers is pointing at the same location. The next thing I want to do is I want to show you a slight modification called voidtypes2.cpp. And what I have highlighted, and I'll show you in the code in a moment, is that I increment the reference pointer by 64 bits, and then I allocate a float. And so here in voidtypes2, this is the same code, this is the same code. But now what I'm doing is because it's void, I have to cast reference to double, add 64 bits to go past the double, and then cast it back to void to add reference. So you can see that the more you have to do this, the more complicated this gets. And then at that specific location where reference is pointing, I add my float value. Then I reset reference to point to the initial location of the double. And then what I'm doing here is I'm printing out the double at the address reference. Then I move past 64 again, and then I print the float at that location. So now what's going to happen at the end when I print the addresses is that numbers is going to be pointing at the initial location, but reference is going to be +8. And the reason why is because a double is 64 bits. It's a double floating point precision number. And then the next value is the float. And we see that what happened is exactly what we expected. +4. Okay. So now what's happening is I've added the values and we have that there. So now I want to show you an animation. Okay, so reference numbers. And this is what's actually going on when I run this code. I say void numbers is allocated. And so here, and I apologize, I skipped over a crucial part. Notice here in malloc that if I want to have a double and a float, I did size of double plus size of float. So it's 8 bytes plus 4 bytes. So a float is a single precision, double is a double floating point precision. And so now it allocates here in this animation 12. Does everybody see that? So then I create a second pointer reference. And it's pointing at the same place. I dereference the reference pointer and store a 64-bit representation of 0.625. Then, in that, I cast the reference to double, add 64 bits, cast back to void to be able to go to a specific address. And then I go to the next line and I put in a 32-bit representation of 1.5625. Then if I actually want to go back, I have to move the reference back up. And then I got to print the double at that specific location. Then I have to move down 8 bytes. And then I have to do that again. So you can see that having to do all of this, so let me go back to the end of this animation. So what I want you to do is I want you to attempt problem 2, and then we're going to discuss how it is that we can get around this challenge of having to write all this procedural programming in something that you're probably familiar with already with structs and eventually with data hiding and classes. Check the anything in the chat. Okay, so who thinks they have the answer? Who would like to share the answer? Yes. B is absolutely right. So what's going to happen here is it's going to start out, it allocates a float, and then it goes and allocates a double. So then we go back, we print the base address, and a float is 4 bytes. So then it will add 4. So the correct answer is B. So very good job. That's absolutely right. All right, so in void node, what I'm going to do is I'm going to start using some of that class, I mean, not class, but pass by reference that you learned in C to see if we can make multiple nodes. So now we're moving up a little bit in the levels of abstraction. What I've done is I said, I want a node size here, and this one can be, it's going to be double, float, and int. So every single node in my node that I'm designing can have a double, a float, and an int. And then I allocate 2 nodes, and that's just going to be 2 void pointers on the data heap, each of which can contain a double, a float, and an integer. And so I'm now going to show you the function for this set node values. I'm passing a void pointer, I'm passing a double, a float, and I'm going to explain why I cast a float in a moment, and I'm going to pass an integer. Does that make sense so far? So now let me show you set void nodes. So up here, I have a procedural, if I want to do this, for any specific pointer. So here, we have void star reference. So this is the fundamental idea of why we call this pass by reference. We need a reference pointer pointing to somewhere on the data heap that I can allocate whatever pieces of information I need. So here we start at the reference with double. Then I have to add 64 bits to get to where I'd want to put the float, which is what we do here. And then I add 32 bits to get to where I would want to put the integer. Does that make sense? So then, now that I can use the modularity of functions, I can just call set node values again and create my second node. So now what I'm going to do is I'm going to call this function print node values, and all I'm doing is passing node 1 by reference. So in node 1 by reference, what I'm doing is I'm going through the same thing, except I'm doing cout, adding double, cout for the float, adding 32 bits, and then doing the same thing for integer. And you can see I say the final address of the reference. So what I'm going to do is I'm now going to compile void node.cpp. And now we see that the initial one here can move. And then the same thing, I do with those values with double, float, and integer. So we see here at the end, they match the addresses of the integer because the reference is moving. So then when I go back, I want to reset it and make sure I'm keeping track of where the base address of the pointer is. Okay, showed you all that. So this is a lot of code. It can be pretty confusing. If you're struggling with it, I don't blame you. Who came to your rescue? Bjarne Stroustrup with C++ and classes. So let's consider what could possibly go wrong if you're trying to keep track of all this. And this addresses a question that has been asked a little earlier, which is, why do we need to keep a reference pointer and a base pointer? And what happens when we take care of all these? What happens when we screw up, basically? So what I want to do is it's the same code, except my print node values does something funky. I have it as double, float, and integer, but notice how, okay, I'm trying to keep track of thousands of lines of code. I accidentally print an integer, then I add the int, I print a float, and then I do a double. So I'm doing them in the wrong order. So what do you think is going to happen? Any ideas? Yes. Absolutely right. So let me run the compilation and show you. Void node bad. We're going to get a bunch of gibberish, a bunch of weird values that we didn't put in. So there has to be some way to be able to keep track of what's going on here. See, we have a question in the chat. Those are, in fact, addresses on the, oh no, they're on the heap. The question is, are those addresses in the stack? And the address is on the data heap because it's data. So we can really screw this up if we're not careful. So this is one of the reasons why C++ ISO standard insists that we cast from void to char star when we're performing pointer arithmetic, because they want you to be absolutely sure. How far do you need to move? You better tell me, because that's going to be stricter, more effective programming. So now the other thing, and this is going to become really helpful for the effective, is just because we print the correct values doesn't mean it's the best possible answer. So what I'm going to show you is that I allocate it correctly on the data heap, but I print it out in the wrong order. But to do that, I have to add, sorry, hold on. Here we go. So in void node bad 2, I allocate it the same way, but then when I print it, I start with the double, then I do reference, and then I go to float, and then I have to move back up. Oh yeah, no, here we go. All right, so here I say double, I move to float, and then I allocate the integer first. You see that? And then I go up to and do the double, and then I go down 1, and then I do the float, which is in the middle. The reason why this is wrong is it'll give us the same answers. It will print out the correct results when I run make void node bad 2. However, what's going to happen is it's going to be inefficient. I have to do 5 pointer arithmetic operations instead of 3. Does everybody see that? So you can either do it wrong or you can do it inefficiently. And so the procedural aspect is I'm doing an inefficient procedure. Does that make sense? I see there's a question being typed up in the chat. Let me bring up the next slide in the meantime. And so there's a reason why this is important. So here, this is the Ariane 5 European Space Agency rocket. And what happened is they were using procedural programming and a programming language called Ada. And what happened is they screwed up a bit shift, and they put the last 32 bits of a double into a float and thought they were just saying it equals. And what ended up happening is it had the rocket had angle detection, and it thought it was going from up to immediately thinking it was sideways. And it had a self-destruct operation, and it would explode, and it cost the European Space Agency $1 billion. Fortunately, no one was on board. They made the exact same error that I had in void node bad. And so I'll do this, and I'll get to the question in the Slack. And so the reason why I want to bring this up is of all the flags in the production quality compilation rules that I have, probably the most controversial in industry is W conversion. W conversion is why I had to cast the float. And in a lot of companies that you'll go and work for, they will never use it because they think it's too restrictive. However, in certain industries, automotive, aerospace, where everything has to be precise to the nth degree, they'll use that because it could be potentially catastrophic if you don't. So what I want you to learn from this is that you have the ability to understand, provided wherever you end up working, why it is that data flows in a specific way. However, if you get to a company and they say, we don't do that, that's perfectly fine. Go with what they want. But you have that knowledge now. All right, so let me take a look at the Slack question. Can you please create a drawing showing how you move up in the code? It's coming quite soon, Lydia. I actually have an animation that will hopefully clarify for that. And when I get through the animation, I will show you. All right, so please take 3 minutes to attempt problems 3 and 4. And I'm just going to go through that void pointer thing really quick, again, in the animation. I'll scroll up here while you all are working on problems 3 and 4. So Lydia, I'll just really quickly show you. So I have the void pointer that I allocate memory. So I have a double and a float. And then I have a reference just purely for that. So I can use that reference pointer if I wanted to call a function. So that way I can make multiple versions of this type of node. From there, I go and I dereference the pointer as a double and then put the actual value that I want to represent. From there, I will perform low-level procedural pointer arithmetic to get to past those 64 bits, and then allocate a float value. Now, if I want to move back up, I move the reference. And the reason why I have a reference as well as numbers is because I don't want to lose track of where that information is on the data heap. So now I can say, all right, I'm going to print a double, and then I perform pointer arithmetic, and then I move down to float. Okay. So Lydia, did that help? Awesome. And again, you are welcome to discuss on the Slack or or with each other. Facundo, did that address your question too? Awesome. Also, I apologize if I butchered your name. Please let me know the correct pronunciation, and I will make sure I get it right for the rest of the semester. Okay, who would like to tell me the answer to number 3? Who was a guest who would like to tell me? Yes. I'm sorry, you had your hand up first. I'll come to you for 4. Yes. C is absolutely right. So what's going on here with print node values is we allocate it as double int float, but I print them as int float and double. So, and the answer is the values will print incorrectly since the pointer arithmetic and print node values results in incorrect evaluation of the allocated data. So absolutely right. And for number 4, I want to give you, whoever it was who had their hand up over here, if you want to try number 4, I'll give you a shot. I'm sorry, I can't hear you. Correct. So what's going to happen is it says double, float, and int. And then we see we do some allocation here. And what's going to happen is that we have the values will print correctly, but ineffectively due to the ineffective pointer arithmetic. Okay, so how do we address these issues? What C++ structs and classes will do for us is it will do all of that work for us. One crucial thing, I'm going to teach you about something called member initialization lists here in a few minutes. And you're going to see that you do them in a specific order will provide that effective allocation of memory on the data heap. So the idea behind a struct in a class, it allows you to encapsulate data, like we talked about in lecture 1, while abstracting procedural complexity. You no longer have to be like when we wrote the code. Well, I didn't write it. I wasn't alive yet. I'm not that old. When we wrote the code that sent the Apollo astronauts to the moon, and you had coders who had stacks of punch cards all the way up here to their heads. And that procedural programming in B, programming language, which eventually became C, it can be very complicated, everything we went through. How can we do this in a way that's effective, easy to program, but you understand what's going on underneath? So you're not one of these quote unquote substandard programmers that Linus Torvalds does. You know what's going on, therefore you'll be the standard, not substandard. So a C++ struct stores each variable to indicate that data belongs to that specific struct, just like we did with node 1 and node 2. It creates a pointer that it abstracts. It does all the work for you underneath the hood. And that pointer is known in C++ by the keyword this. You can see that I have it highlighted in red here. The this pointer will serve as that base pointer, and any arithmetic that's going on, the struct and the class will create its own reference pointer to be able to access the information. I see we have a question in the chat. Megan, for problem 2, it's because of the float instead of the double. All right, so does everybody, I'm going to show you some animations about the this keyword and how we allocate memory on the heap. All right, so the basic idea behind a struct is you have a struct, and then you have the name that you're going to name it. This might be review, but I just want to go over it again. Then you have the struct private members, and then you would have what we're going to call the constructor. And that constructor is going to be a C++ way for us to allocate all that memory on the data heap. And then we're going to have struct methods. And the idea behind the struct methods is that these are operations that you can perform on the struct information. And so short version, it constructs data on the heap. And you can see that I have data structures there. So this is a fundamental data structure that we're building now. And so a constructor is a specific kind of member function that's used to create a new object. So we're going to call classes object, and those objects have private members. So a node is a type of object. And the node that we created had a double, a float, and an integer. So now we're going to let the struct do the work for us. And so what I'm going to do is I'm going to show you the syntax of a constructor. The main idea, and I'm going to go over this over and over again for the next couple of lectures before you really have to dig into Coding Challenge 2, so hopefully this will clarify. A constructor has the same name as the struct or the class, and then you can have either 0 or more inputs. And what that does is it takes the inputs and it stores those inputs as copies on the data heap. And it has no return type. Does anybody have any questions on that before I show you a struct example? Okay, so I always feel like there's like animals running across this. So this is an example called struct simple. And so the idea here is you have the keyword struct, and then whatever you want to call the struct is what you put next. So in this case, for consistency, I'm going to call it node. And then after that, I have the struct members, double, float, and int. The next thing I'm going to do is show you the constructor. So I want to take you through this step by step. And what's going on is it has the same name as the struct. And then I have inputs double, double in, float, float in, and int, int, in. So what that means is I'm taking inputs to my constructor. And the next thing I'm going to show you a slide to clarify is what's known as a member initialization list. And what it does is we go through in the order here, we go the double, float, and int, and we assign the values to our private members. So what you do is you have in, just like you did with a function, the inputs, and then you do a colon. You can either have this up here or you can press enter. Either is fine, depending on what you think is easier to read. And then I say the double. I'm going to map the value as double in. When I have a float in, I have a comma, then the float is set equal to float in, then comma, the int is set to value of int in. Does that make sense so far? All right, so what I like to do is like to show you the slide where I describe this in detail as well. So the member initialization list is an alternative way of defining constructors. So I'm going to show you an example here that the production quality compilation rules has you put the member initialization list in the same order that you create the members in the struct. Does anybody have a guess as to why, other than the summation that I have in the slide? I'll give you a hint. We just spent a lot of time dealing with data heap stuff and efficiency. Yes. Absolutely right. We want to make sure that we're doing effective pointer arithmetic. So by making this member initialization list in the same order, you are making efficient construction of a struct. And if you're creating hundreds or thousands of these, this will save your whole program significant amounts of time. So even though you might use a class and you might, with a couple of programming challenge exceptions, never touch a void pointer again, understanding how they work will lead you to write effective production quality classes. And so the format struct variable, input variable. If we were doing it inside, it would be struct variable equals input variable. So I want to show you the equivalent. Here on the left, we had that set node function where we passed a reference pointer. Now that I have a class, I don't need to do that. It creates the reference pointer for me. It keeps track of where everything is on the data heap for me, and it allocates everything in order, so I don't need to write complicated pointer arithmetic. So that's the one I showed you here, where it had the node constructor, and it's doing the exact same thing at a different level of abstraction. Okay, so we have a question in the chat. Is there a reason why the constructor uses parentheses and not assignment operators? So Aiden, this is the member initialization list is what's considered, quote, better practice in industry. And more importantly, you can use this to just do the values as you're allocating the memory. If you want to perform any other operations beyond allocating in memory, you may put the elements inside the brackets there. So for example, you're asking about this, right? Where we have here, and I don't have it as the double equals double in inside of a bracket here. So that we can separate the allocation of memory and any other operation. Did that address your question, Aiden? Awesome. All right, so let me continue. And so to emphasize the idea of this keyword again, the keyword represents the location pointed to, and it's very much like a void pointer. It stores the base address of the pointer, which contains the base address of the struct. And so if I'm going to show you a struct method here called print node values, and what's going to happen is I'm going to show you different levels of abstraction here. Down here, the initial address of this prints out the base address of the struct on the data heap. And then if I say double, I can actually do this arrow double. I'm going to kind of go over this a little fast because I'm going to show you the higher level of abstraction where it starts out with this pointer, and that is actually performing the pointer arithmetic to get double. And then I can just print the address that gives me the address of the double. When I say this float, the float, it's performing that same pointer arithmetic to get to the float, and then I'm going to print out the address, and I'm going to do the same thing for the integer. Does that make sense? So I can use this keyword to do everything. So here I have two nodes that I'm creating with my constructors. Let me zoom in a little so it's a little clearer. And then I'm going to also say the node is at address ampersand node. This is going to give me the same value of this pointer that's inside that register. So it's all kind of feeding back with each other. So what's going to print out is the address of node 1. And then when I call print node values, what's going to happen is it's going to print out the this pointer and then double, float, and int. And we're going to see that the ampersand node 1, this, and then ampersand this, the double, are the same address because where the double begins is there at that location. So let me run it, and then I'll take questions. So this is make struct simple. And we see that as we expected, the node is at, it ends with 1 echo 0. We see that the initial address of this also ends with 1 echo 0. And then double was 1 echo 0. We add 8 bytes, and we get a float. And then we add 4 more, and then hexadecimal, for those who may not know, C is 12 in hex. And then we do the same thing for node 2. So it's allocating different locations on the data heap. Okay. So now I want to take this up even a little higher in the levels of abstraction. It turns out to access all of that, we don't need to do the this arrow in front of either the address or the values. The C++ compiler is treating it as an object and does the work for you. So here it's the exact same thing, except if I put this arrow in front, it will still compile and run exactly the same. The objective there is as abstracting complexity from the program. So you don't have to do that, but it's good to know why it is that that does work. So I would compile it, and it would give me the exact same thing. Okay, so struct is an abstracted C++-oriented object approach to allocating memory on the heap and then keeping track of the location using a pointer known as this. Okay, so struct mod. Now, the one thing that I do in struct mod.cpp, so I want to take you down to main. I'm going to show you a modification. I print the values, and notice here at lines 52 through 54 that I have dot the double, dot the float, and dot the int. And I change the values, and then I would print everything again, and the values would be updated. What's going on there is that structs have public members, meaning that you can access them and make changes. And that allows you, and sometimes, and we'll see this when we get into specific types of data structures, that using a struct in a particular scope is beneficial. However, that's not always the case. Sometimes you don't want certain users to be able to change certain pieces of data. We need to have a level of data security. So what the C++ solution is, okay, so there's the C++ solution is to develop a class. The difference between a class and a struct is that the members of the class are by definition private, meaning that after you construct the class, they cannot be accessed unless you have what we're going to call get or set methods. A get method will return a copy of the private member. A set allows you to pass an input, and you can regulate which ones that you want to do. So what I want to do is I'm going to, if you want to, when you study back, there's the class node versus struct node. And the only difference is that I have these two keywords, private and public. Private, I have set the private members, double, the float, the int. And then I have a public constructor and a public print nodes method. So let me show you that code in up close so it's a little easier to see. You can see that I have them set privately. And then I have the public, and we do all the same stuff. And so I'm going to run make class node, and we're going to see that I'm able to access these values and print out the addresses. So the difference here is at the bottom. I'm sorry, no, these are the two nodes. So that does it. Before I go on, does anybody have any questions about a class and how that's working? So class is doing the same thing underneath the hood. So now what I want to do, and hopefully, let's see, it was Lydia. So Lydia, this will hopefully clarify everything that's going on with a class. So what I'm going to do is I'm going to create two class objects and allocate the memory on the stack, the registers, and the heap. And I'm going to go through and briefly explain what's actually going on. So in main, you're going to see under registers that I have stack pointer, and I create a copy of the main code and I put it in the stack. And in the stack pointer, it right now is pointing to main. And that's what I called at the beginning of the semester the program counter. So now what I do is I would move down to this piece of code. I would make a copy of the code on the stack. And then what I'm going to do is I'm going to go to the constructor. And in the constructor, I'm going to create the this pointer that is pointing to the location of the base address of the class on the data heap. And then I need to create a reference pointer to allocate them in order. Does everybody see that? Awesome. So now, I'll get to Matt's question in a second. So now what's going to happen is now that I'm done with the constructor, I'm going to remove that copy of the code off of the stack, and then I'm going to go to the next location in main where I create node 2. So now I'm creating a second class object on the data heap. What's going to happen is I'm going to create another register, and I just want to point out at the bottom here that node 1 and node 2 are spaced out for animation clarity, just so it's clear what's going on. It's not necessarily that you keep them separate, that's just a visual choice. But now I go through the same thing. I go double, and I do that. I create another reference pointer underneath the hood. Then I add 64 bits. I do a float, and then I add in another integer. So let me address Matt's question before we continue. Why do you typecast float and not int or double? Okay, so to go over the thing about the Ariane 5 space rocket, a computer, in the Notre Dame computing machines, when you put in a decimal point, by default, it creates it as a double. And then, so it's going to make a 64-bit version of the digit, and then you try saving it as a float. If you don't cast it, there's the potential of losing information, losing precision. So by casting it to float, what's going to happen is it's going to say, make it a 32-bit first, and you preserve precision. So Matt, did that address your question? Awesome. Okay, so this is what's going on. And then you see here when I do ampersand node 1, it's printing the value inside the this register. And if I print the node values, you see that it prints the same thing. If I go to double, it gives me the full value. If I say ampersand double, it gives me the address, the base address, which actually happens to be the same as this, the float, and it gives me the base address and the int and the base address of the integer. So last thing, I'm going to skip over nodes 2 because it does the same thing. And I'm going to show you what happens with return 0. With return 0, the first thing it's going to do is it's going to free the memory on the data heap as well as the registers. And then it's going to free the instructions from the instruction stack. And then free the stack pointer, and now it's available for the operating system to give us the next program. All right, so please take a couple of minutes and attempt problems 5 and 6. Actually, do 5, 6, and 7, please. I think you already know enough to figure it out. And 7's the last problem, so once you're done, you're free to submit. While you're doing that, I'll remind you that it's free unlimited submissions. You're encouraged to do so. If you come to class and you put in the work, please don't lose the points. I want to make sure you get credit for the work you're putting in. The benefit to you is the attempt to learn and build your skill, your knowledge. So please do 5 through 7. All right, who would like to share with me their answer for number 5? Anybody have any guesses? It's no shame. Give it a try. Who would like to try? Yes. A is absolutely right. We have the same thing where we have the 3 inputs. We have the member initialization list in the exact order to ensure efficiency. So what about number 6? What was going on here with number 6? What do we expect there? Yes. B? B is correct. Very good. So we have prints out this pointer, and it prints out the values. We have to add 8 to get to the float, and we add 4 more to get to the integer. Last question. Who wants to, what's the, we say it's not going to compile. What do we expect the reason why? Does anybody have any guesses? Yes, in the back. Yes, C should be, the input values in the constructor are matched in a different order than they are allocated on the data heap. And let me acknowledge the person in the chat who mentioned it, probably also the same thing. Yes, same thing, it's C. And so we put it in, it's allocated correctly, but inefficiently. The ISO rules strictly enforce it. So outstanding, great job. Was that a good pace today? All right, good. I apologize for, I felt like I had to rush the last 5 minutes of lecture. This is the pace that I prefer to go at, and this will be the rest of the semester. So keep up the outstanding work. I'm really happy with how everybody did on the labs and how everybody's been doing on the lecture notes. Please make sure to submit them. You're allowed to have unlimited submissions until midnight tonight. And on that note, it is 2 o'clock and you are dismissed. Let me turn off this.